So let's look at another kind of combination problem. We've got three capacitors, 1, 2, and 3, but this time we have a switch that first connects to point A, which means we've got the battery in the circuit, and then it flips over to point B. So what's happening during this circuit? Afterwards, so after it's flipped to position B, what's the charge on the potential difference across all three capacitors? So we've got to think about what's going on. Let's look at what's happening in the initial case. So the initial is when the switch is in position A. If the switch is in position A, at part B it's not connected, so no charge can flow through this part of the circuit because there's no connection. Charge can only flow when the wires are all connected. So over here, no charge can flow. That means it's like this is not even part of the circuit. We could redraw this entire thing and we could just leave that branch off. So an equivalent, we get exactly the same behavior if we only have the 100-volt battery and capacitor C1. This is exactly the same thing. Okay, hopefully that makes sense. If it's not connected, we got no action over here. It's like they're not even part of the circuit. So if this is our circuit initially, we have a single capacitor connected to a battery. We know that the potential across the capacitor is going to be the same as the potential across the battery. So delta V1 initial is going to be 100 volts. Our capacitance C1 is 12 microfarads, which means we can find the charge on capacitor 1 initially is going to be equal to C1 times delta V1 initial. So it's going to be 12 times 10 to the minus 6 times 100 to give us 1.2 times 10 to the minus 3 coulombs. So at the very beginning, the total amount of charge on this capacitor, charge stored on this capacitor is 1.2 times 10 to the minus 3 coulombs. Okay, that's our initial state. Next, what happens is we flip that switch. Let's see what happens then. So our initial was with the switch flipped at A, and we figured out what happened then. Then what happens is we flip our switch to position B. So the switch now gets flipped over here. Let's redraw what that looks like. That means we've got our battery here, C1 here, and now we're connected to C2 and C3 over here. C1, C2, C3. So this is what it looks like with the switch flipped to position B. If we look at what's happening here, now the battery is no longer connected. This is no longer part of the circuit. So we could draw an equivalent that says we only have C1 and it's connected to C2 and C3. And we see that C2 and C3 are in parallel. So here's C1. C1 is all charged up. It's got a charge of 1.2 times 10 to the minus 3 coulombs, and it's got a potential of 100 volts. That's what happens as soon as we flip to B. And then we've got capacitors C2 and C3 here. So what happens in this situation? C1 is all charged up, C2 and C3 aren't. That means C1 acts like a battery, and that's what a capacitor does. It stores energy, it stores charge, which it provides to the circuit once it becomes connected. So what's going to happen is that this is going to provide charge and potential to the other capacitors. Okay, so let's get that down in a note. So after the switch is flipped, C1 is fully charged, which means it acts like a battery. And it is connected to C2 and C3, which are connected in series. Okay, if these two are connected in series, let's do an equivalent and draw an equivalent circuit. Let's start by drawing the equivalent circuit here. So the equivalent circuit means we take out C2, we take out C3, and we replace it with an equivalent capacitor. We could call it CEQ. I think I'm going to call it C23 to remind myself that it's the equivalent capacitance of C2 and C3 combined. So to add capacitors in series, I know 1 over C23 is 1 over C2 plus 1 over C3. C2 was 4 microfarads. C3 was 6 microfarads. So I've got 1 over 4 plus 1 over 6. That's the same as 3 over 12 plus 2 over 12, or 5 over 12. If you're a numbers person, you might just do that on your calculator. I'm more of a fractions person. So C23 is 12 microfarads divided by 5, or 2.4 microfarads times 10 to the minus 6 farads. Okay, now let's think about the logistics of this circuit. What's going to happen? C1 acts as a battery. It has a bunch of charge on it. What's going to happen is that charge is going to flow around this circuit. So this charge here is going to redistribute until it's over both capacitors. And it's going to redistribute until these two have exactly the same potential, because these two things will need to have the same potential. This one's going to supply potential. Whatever gets supplied gets used up. Okay, let's make a list of what we just said. So we said that the potential across 1 and the potential across the equivalent of 2, 3 is going to be the same. And the total charge is going to be the charge on capacitor C1 plus the charge on capacitor 2, 3. And all that charge came from what was already on C1 as we got started. So that's going to be 1.2 times 10 to the minus 3 coulombs. And the way we're going to put all this together is we're going to use the equation that charge is equal to capacitance times potential. Okay, let's start to work out this bit. I'm going to start with my expression for conservation of charge, that the total charge is split over the two capacitors. So I know that my charge on capacitor C1 plus my charge on the equivalent capacitance C23 has to add up to give me 1.2 times 10 to the minus 3 coulombs. Next, I'm going to use the equation that charge is capacitance times potential. So Q1 is C1 times the potential across capacitor C1 plus Q23, which is going to be my equivalent capacitance, C23, times the potential across my equivalent capacitance. But remember, that has to have the same potential as C1. These two have to have the same potential. So instead of writing down delta V23, I'm going to write down delta V1 because they have to be the same. Okay, so now the only thing I don't know in this expression is delta V1. So I'm going to solve for delta V1. Delta V1 is 1.2 times 10 to the minus 3 coulombs divided by C1 plus C23. So 1.2 times 10 to the minus 3 coulombs. C1 was 12 microfarads, so 12 times 10 to the minus 6 farads. Plus C23, C23, remember, was 2.4 times 10 to the minus 6 farads. That gives me my potential across capacitor 1. Delta V1 is equal to 83.3 volts. Okay, this is going to be the same as the potential across the equivalent capacitance, C23. So next, with this number, with the potential, I can find the charge over C1 and I can find the charge stored on C23. Okay, so let's do that next. So my charge on capacitor C1 is equal to C1 times delta V1. C1 is 12 microfarads, 12 times 10 to the minus 6 farads, times delta V1. Delta V1 is 83.3 volts. That gives me a charge on that capacitor of 1 times 10 to the minus 3 coulombs. Then there's two ways to find the other charge. I can do C23 times delta V23, or I can do 1.2 times 10 to the minus 3, subtract this number. Two ways to do it. Both are fine. Both are correct. Just to keep it looking nice, I think I'll just use the equation again. So my equivalent capacitance, 2.4 times 10 to the minus 6 farads, times the potential across that equivalent capacitance, 8.33 volts, 83.3 volts, gives me a charge across that capacitor of 0.2 times 10 to the minus 3, or 2 times 10 to the minus 4 coulombs. Okay, let's take stock. I now know the charge and potential of capacitor C1. I know the charge and potential of the equivalent capacitance C23, but that's not what I was asked for. I was asked for the charge and the capacitance across C2 and for C3. So let's break that down next. So we're at the finishing steps now. I've already got all my information gathered about C1. For capacitor C1, it carries charge Q1 equals 1 times 10 to the minus 3 coulombs. It has a potential difference across the plates of 83.3 volts. Now I'm trying to find the information about C2 and C3. Well, what I know is that C2 and C3 are connected in series. The series equivalent is C23. What that means is that C23, C2, and C3 all have the same charge because it's all a series connection. So when we have things in series, it means the same charge. So what that tells us is that Q2 equals Q23 equals 2 times 10 to the minus 4 coulombs. So this is our information for capacitor C2. For capacitor C3, charge Q3 is the same as charge Q23, same as charge Q, 2 times 10 to the minus 4 coulombs. All right, what about the potentials? Well, we know our potential, delta V2, is going to be our charge on capacitor 2 divided by capacitance 2. So our charge is 2 times 10 to the minus 4 coulombs divided by capacitance 2, which was 4 microfarads. That gives us a potential across capacitor 2 of 50 volts. For our potential across capacitor 3, delta V3, we've got charge 3 divided by capacitance 3, 2 times 10 to the minus 4 coulombs, divided by capacitance 3 was 6 microfarads, 6 times 10 to the minus 6 farads, gives us a potential across capacitor 3 of 33.3 volts. Okay, now we've found the charge and potential for each of those three capacitors. Here's another problem. It's a little bit similar to the last one, not entirely the same, but similar. I'm going to leave this one as a homework problem for you, but I will post an extra video just walking you through the setup in case you find this concept of applying the switch difficult.